Picture a small roadside stall. On the first day, you buy 2 samosas and 1 tea and you pay 40 rupees. On the second day, 1 samosa and 1 tea and you pay 25 rupees. Nobody ever told you the price of a single samosa or a single tea, and yet you think, I can work this out. You're using two simple conditions at once to pin down two unknowns. That is a system of linear equations, and we're about to learn a clean way to solve any of them. Let's be precise about the pieces. A linear equation looks like this. Known numbers multiplying the variables added together equal to another known number. The numbers in front are the coefficients. The lone number on the right, b, is the constant. Linear means every variable appears just to the first power. No squares, no products, nothing curved. Stack several such equations, all sharing the same variables, and you have a system. Let S be the price of a samosa and T the price of a tea. 2 samosas plus a tea is 40. One of each is 25. A solution is any pair of prices making both statements true at once. Not one, but both. That word, both, is the whole game. Before any algebra, let's see what a system means. Each equation in two variables draws a straight line. So two equations are two lines, and a solution is exactly where they cross. When the two lines meet at a single point, that point is the only pair satisfying both. Exactly one solution, a unique answer. But the lines might never meet. If they're parallel, same slope, shifted apart, no point lies on both. The system is inconsistent, no solution. And there's a third, sneakier case. The two equations might be the same line drawn twice, one just a multiple of the other. Then every point on that line works. Infinitely many solutions. So every system falls into exactly one of three fates. One answer, none, or endlessly many. Our method is a machine for telling them apart and finding the answer when one exists. The same picture lifts into three dimensions. With three variables, each equation is no longer a line. It's a flat plane in space. Three equations, three planes. When all three planes slice through one common point, that point is the unique solution, the one triple lying on every plane at once. But the three planes could instead share a whole common line. Every point on it satisfies all three, giving infinitely many solutions. Or they can be arranged so no single point lies on all three at once, and then there's no solution. Writing all those variables over and over gets clumsy. So we pack the system into matrices. The coefficients become A, the unknowns S and T become X, and the right-hand numbers become B, and the whole system collapses to three tidy symbols. AX equals B. For the elimination, we glue A and B together into one grid, the augmented matrix. The dashed line just marks which column used to be the right-hand side. Now every move happens on these numbers alone. Gaussian elimination rests on three moves, and only three. Each one rewrites the system without changing its solution. So we can simplify freely. Move 1. Swap two rows. Reordering the equations obviously can't change which prices solve them. Move 2. Multiply a whole row by any non-zero number. Scaling an equation on both sides keeps it the same equation. And move 3. The workhorse. Replace a row by itself plus a multiple of another row. This is how we knock entries down to 0, one at a time. Now the real thing, a 3 by 3 system, solved end to end. 3 equations, 3 unknowns. Watch every number. Here's its augmented matrix. The plan? Carve a staircase of zeros beneath the diagonal, working left to right. Our first pivot is the one in the top left corner. We use it to wipe out the column below. Row 2 starts with a 2, so subtract 2 times row 1. Row 3 starts with a 3, so subtract 3 times row 1. Row 2 becomes 0. 1 minus 3 minus 7. Row 3 becomes 0, minus 4, minus 1, minus 11. The first column below the pivot is now 0. On to the second column. The next pivot is the one in row 2. Below it is a minus 4. So add 4 times row 2 to row 3. That gives 0, 0, minus 13, minus 39. Look at the shape now. A clean staircase, zeros filling the lower left triangle. This is row echelon form. The forward march is done. Now we climb back up. Back substitution. The bottom row says minus 13z equals minus 39. So z is 3. Slide up. Y minus 3z equals minus 7 gives y equals 2. And the top row x plus y plus z equals 6 gives x equals 1. Our unique solution 1, 2, 3. And we never just trust it. We check. 1 plus 2 plus 3 is 6. 2 plus 6 minus 3 is 5. 3 minus 2 plus 6 is 7. All three hold, verified. Elimination doesn't just find answers. It also tells you honestly when there aren't any. Take x plus y equals 2 and 2x plus 2y equals 5. The second row is exactly twice the first on the left. So subtract 2 times row 1 from row 2. The left side wipes 2, 0 and 0. But the right side is 5 minus 4, a stubborn 1. Read that last row out loud. 0x plus 0y equals 1. That says 0 equals 1, which is never true. No pair of numbers can rescue it. So the system has no solution. Those are our parallel lines, algebraically. Change just one number. Make the right side 4 instead of 5, and everything shifts. Now the second equation is precisely 2 times the first. Same row operation. Subtract 2 times row 1 from row 2. This time the right side is 4 minus 4, 0. The entire bottom row vanishes to all zeros. A row of all zeros reads 0 equals 0, always true, telling us nothing new. That equation was just a copy. We're left with one real constraint. X plus y equals 2. One equation, two unknowns. So one variable is free. Name that freedom with a parameter. Let y equal t, any real number. Then x is forced to be 2 minus t. So the solutions are every pair to minus t, slide t, and you walk right along the shared line. Infinitely many answers, all captured in one neat formula. Now freedom in 3 variables? Look closely. The second equation is double the first. The third is triple it. They only look like 3 different constraints. Clear column 1. Subtract 2 times row 1 from row 2, 3 times row 1 from row 3. Both rows collapse entirely 2 zeros. Even on the right, 2 whole rows became 0 equals 0. Only one genuine equation survives. X plus 2y minus z equals 1. But there are 3 variables to pin down. One equation, 3 unknowns means 2 are free. Column 1 has a pivot, so x is determined. But columns 2 and 3 have no pivot, so y and z roam free. Call them s and t. Then x is 1 minus 2s plus t. The complete solution is that triple, a whole plane of answers. Sanity check. Pick s0, t0, and you get 1, 0, which satisfies all 3 equations. Every choice of s and t lands on a real solution. Your turn. Here's a fresh 3-battery system. Pause the video, form the augmented matrix, and run the elimination yourself before I do. Here's the walkthrough. Clear the first column. Row 2 minus to row 1 is 0, minus 3, minus 1, minus 9. Row 3 minus row 1 is 0, 1, minus 2, minus 4. Now clear the second column. To keep whole numbers, take 3 times row 3 plus row 2, which gives 0, 0, minus 7, minus 21. That last row is our final pivot. Back substitute up the staircase. Minus 7z equals minus 21. So z is 3. Then y is 2, and the top row gives x equals 1. The answer is 1, 2, 3. If you got that, you've genuinely mastered elimination. Trap 1. Misreading a 0 row. A row of all zeros, constant included, just means 0 equals 0, a redundant equation. It never means no solution. It signals a free variable. Trap 2. Missing the inconsistency. If the left side is all zeros, but the constant is not, that's 0 equals C impossible. That's the true no solution signal. Trap 3. Forgetting free variables. Any column without a pivot is free. Give it its own parameter. Skip that, and you'll report one answer when there are infinitely many. And trap 4. Silent arithmetic slips. Write the scaled row out in full before subtracting. One flipped sign can turn a unique answer into a phantom no solution. Let's lock it all in. Write the system as a x equals b, then pack it into the augmented matrix. Run the row operations forward until you reach row echelon form, that staircase of pivots. Then read the outcome of the rows. A row saying 0 equals a non-zero number means no solution. A pivot in every variable column means each unknown is nailed down. Exactly one solution. And a column with no pivot means a free variable and infinitely many solutions. Master those steps, and no linear system will stump you again.